Hello, everyone. My name is Aaron. I'm from the University of Cambridge. I share equal contribution with my course Ilya in this piece of work. Until a week ago, it should have been Ilya to come here to present the talk, but apparently he cannot get his American visa. So I'm somehow happy to be here to present our work. This is a piece of empirical work looking at the interactions between adversarial attacks and neural network compression. In this talk, I will divide it into two parts. In the first part, I will show the empirical results we have. In the second part, I'm going to introduce you a defense that we developed, which is inspired by this piece of work. I hope at the end of this talk, I can persuade you that neural network compression will make adversarial attacks easier. So what's happening today is we have over 1 billion devices, and many of them have great compute and memory resources on them. So, for example, a smartphone, right? It's in both in my pocket and probably in your pocket. So many of them are currently or will be soon running some machine learning workload. For that, we mean they will run some form of compressed neural networks. In terms of regulations here, we have some safety guarantees on those devices because your phone does not blow up easily. But in terms of security, there's pretty little or no security on them. What happens with machine learning now is machine learning is everywhere. And in machine learning, we operate based on data. If your classifier is not showing the correct accuracy, what do is we sometimes fix the neural network itself, or most likely you pump it with more data if you have the data. Then that means we're introducing a lot of noise or non-determinism into this system. Then it is really hard now to define security. So why we think adversarial attacks are possible? Our simple view is that first, your data set is very questionable. If we look at even this toy data set, the very popular MNIST data set, we have those images in our data set. To be honest, as a human, I cannot tell what numbers they are. And a lot of time also, when you're training the models, what happens is you pick your favorite checkpoint, and also you pick your favorite neural network architecture, and a lot of time our model is actually overfitting our data. So this gives the chance of adversarial samples. What do we mean by adversarial sample? Is a sample that generated from the original image and with some handcrafted noise. And now, I can still tell it's a rabbit, but apparently my neural network will tell it's something else. And it suddenly opens a whole taxonomy of attackers here. We can generate samples that are, we can generate adversarial images that are pretty easy to do by using attack that's probably single-step attack. It's probably very portable in real life, but the perturbation you generated is pretty large. And also, sometimes if you apply iterative attacks, in this case, you get very small perturbation that human can hardly tell. So what's more important is that we realized those adversarials, if the adversarial samples generated can be successfully fully used on the second classifier, that pretty much means those two classifiers share similar feature space, or at least they operate on similar feature spaces. And one thing, sorry, I forgot to mention that there's also another type of attack we call reprogramming, is where the attacker plays a constant noise onto your data set, and suddenly the whole classifier is doing something else. For example, the classifier used to be applied to recognize road signs, and I reprogrammed my neural network using adversarial samples. Now it's recognizing rabbits. Well, surely there are security concerns behind those things. And many of us will think, since I've mentioned we have over 1 billion devices, surely those networks are diverse. And we have to realize that most of the time when we run models into those devices, we run slimmed down versions of them. Because the performance is a critical issue on those devices. What do we mean by compression in this case? We mean quantization. We mean quantization is to change your number representation to something simpler so that you execute in a nicer data format, for example, fixed point or even powers of 2 weights. And also pruning means we take off some unimportant connections in your neural network and then you retrain them. And also you can do low-rank approximation using singular value decomposition, and also to some extreme case, people do binary and ternary weights to further save the memory and compute requirements. So what happens in real life is most of those compressed neural networks have the same ancestor model, that's what we call, or you can understand as the baseline model. And why this happens is first, data costs money, of course, and also labeling data is pretty expensive. And surely, what you do not want to do is to partition your data for different classifiers, because that directly decreases the performance of those classifiers. And this raises a question for us. If you have the networks that share the same ancestor model, are they still attackable? This is the first question. And the second question we're trying to answer is, how do those adversarial samples survive from compression processes? So we consider the two attack scenarios in this case. In the first case, we generate adversarial samples from the ancestor model, or we call the baseline model. And then we use those adversarial samples on different compressed neural networks. And what we also do is we generate adversarial samples from different compressed models and then apply them on the baseline model. Our intuition is that if those two attack scenarios hold true, what that means is from an arbitrarily compressed neural network, I can now generate adversarial samples that can be successfully transferable to the networks that have the same heritage. And we generated all these compressed networks using the tool Mail we've developed. This is a tool that can help you to generate help to chain up different compression methods. And why we think this problem is important, taking like a very simple example, is if there's a CCTV camera company and they produce two lines of products, one's bank camera and one's cameras that's for your cats, right? And of course, like attacker might find it easy to access to a home use camera that's watching your cats. And if the CCTV camera company is using the same set of ancestor model for those two different cameras, and surely the adversarial sample now generated from the home use camera can successfully transfer to the bank camera. And this is a very serious security threat there. So in this case, I'm showing you some results when we apply fine-grained pruning. And fine-grained pruning is a method that takes off unimportant connections in your neural network. And it will save bandwidth and also save compute if you have a sparse matrix accelerator somewhere on your device. What we observe is we have marginal protection, meaning that the accuracy increases a bit at the preferred density. What do we mean by the preferred density is the density that your classification accuracy just starts to decay. So that's the smallest density where you can still have the acceptable, still maintain the classification accuracy there. And of course, in the red line, we see it increases because when at near zero density, our classifier is generating garbage outputs. And if you generate adversarial sample based on those garbage outputs, surely those adversarial samples will not transfer to the baseline model. Then when you look at fixed point quantization, what we observe is literally a flat line. That means all the attacks are transferable at high precision. But we observe like a marginal increase in the accuracy when we found like when we use a bit width of 4. But when at the bit width of 4, we're decreasing the integer bit width. Effectively, what happens on your activation is those activations are clipped because now they have a very restricted numerical range. I will elaborate on that a bit later. Then, what we think really interesting is if we consider a different baseline as a model that has been trained twice with different initializations, if we consider an attack that's not even that transferable, which is a deep fault attack in this case, under the net5 model, we show a changing accuracy of 93%. What does that mean is we get the accuracy on the source model where we generated the adversarial sample from, and then use that adversarial sample to be evaluated on the target model. And then this is the difference in this accuracy. And surely this attack itself is not that transferable, but it shows great transferability when we consider a baseline to both pruned and quantized model. What that means is, apparently, you may ask, how do you get the pruned and quantized models? Well, I'm telling you, we used fine-tuning. So basically, we take the model and then retrain it. And apparently, the feature space in our intuition is that it maintains to be as the same feature space. So the takeaways here is that transferability survives when the compression during the compression process, both in terms of pruning and quantization. And we observe something interesting is the clipping of your activation. When your activation clips, it turns out that we have a margin of protection. In our intuition, what happens is that most of the attacks are trying to drive some activations to some unwanted states. And if now your activations can saturate to certain value, the attack will have less chance to boost certain activations to really large value so that it can basically dominate the feature space. So then we're thinking of whether we can develop a defense based on this observed behavior. So let's take a step back and look at what does existing defense do. And we have some popular methods like adversarial training. In this case, you have lots of retraining, and you have to have some prior knowledge of your attackers. In the second case, people are working on detecting adversarial samples. Works like magnet and safety net use external classifiers on top of the existing CNN, so that they can decide whether the incoming sample is adversarial or not. But on constrained devices, none of these methods really work that well, because you don't really want to add additional classifier that's probably very large, or you don't want to make substantial change to your neural network architecture. So here we present the solution we had. We call this a taboo trap. What a taboo means is a hidden command that only the receiver and the sender knows. And if it is, so a give example is like you teach your kid good manner, and one day your kid suddenly start to swear to you on the dining table. You know this must come from really bad influence, also known as the attacker. So in this case, we train our neural network to behave in a certain way by avoiding certain activation range. And if a sample count and our activation falls into that range, we know this is the attacker. And this becomes really interesting because now we can use different combinations of range on different locations of your activation. Essentially, we're introducing a crypto key here. So just like as you imagine, if we have a key, we can perform many cool things. And this is just an example showing on the heat map. We're designing this restriction on activation values based on polynomial functions. And apparently different coefficients now on this second order polynomial can become your keys. What we're showing here is when two keys are very similar, the adversarial samples are transferable. But if the two keys are very different, the adversarial samples can be less transferable. So it is now a matter for you to choose the right key. And also what's interesting as in security is if we have keys now, we can do keys attribution. Meaning that if we have certain classes of devices and each of them have different key, and if I know this certain class of device has been broken down, by gathering the key and also the adversarial sample, I know exactly which is the class of devices that has been broken down. So then the vendor can issue a patch to those devices or just recall them. So this is the end of my talk. Thanks for listening.
Hi, Nicholas Carlini, Google.
Hello.
So talking about the last couple slides, you mentioned that you can use keys in this way.
Right.
So first of all, detection is actually very hard. Most people who have tried to detect have failed. Magnet and safety net don't work. Going to your question, when you have keys, how do you make sure that I can't extract the key by querying your model?
Sorry, are you talking, what do you mean by extract?
So you said like you have keys in these networks, like crypto keys?
Yeah.
When we design crypto systems, we make sure that even if I can have you do like a chosen plain text that the key is safe.
Yeah.
How do you make sure the key is safe in this setting?
Currently, we don't have a solution. What we do right now is we just show there's a possibility of inputting a key there.
Okay.
Right.
Do you have any other questions? So I have one last question. So if, with respect to the question of transferability, if you use one of those techniques that retrain the model once you quantize, like decompression, for example, but instead of like training with mini-batch stochastic gradient, you were doing like robust adversarial training, where you were training on adversarial examples, do you still see that sort of transferability?
We tried that. It's not in our paper, but we tried that offline. We see some protection. But what do you mean is, do you put all the, but we didn't try to use adversarial training to include the quantized model in the line. We just tried that with the baseline model. So in that case, it's still transferable. But I guess what you say could be something to be tried as well.
Well, any other questions? Well, before we enjoy the break, let's thank all the speakers in this session.
Thanks.